right, I think we're ready to start. Good afternoon, everyone. Welcome to the Frontier of AI panel. We've got a STEAM panel here, and we've got a lot to cover, so I'm going to jump into it. We're going to focus today's conversation around three pillars that we've identified that we want to cover today. The first of those is architectures, second, energy efficiency, and then finally, trustworthiness. And so, as we've seen from new model designs, diffusion architectures, all the way to brain-inspired and edge-optimized systems, our panelists will explore how we can make AI not only more powerful, but also more efficient, more reliable, and aligned with human values. It's about rethinking what intelligence means in our machines and in ourselves. So without further ado, I'd like to introduce our panelists. Yiren Chen, he's the director of Athena, pioneering energy efficiency, edge computing, and scalable AI systems. Next, Adam Clivens, director of IFML, advancing the foundations of learning architectures and efficient training to impact the design and use of practical AI systems. Zach Bitkow, associate director of ARNI, bridging neuroscience and AI to uncover brain-inspired computation. And Shenzhang Zai, co-director of Invite, leading work in trustworthy, neurosymbolic, and human-centered AI. Each of our panelists have prepared a short summary of their work, and so I'm going to turn that over to them. If you could advance the slide, and we will get started in that section. After this, we'll do a little bit of a Q&A amongst the panel, and then we hope to open it up for questions. Okay.
Or you can stay seated, whatever.
Okay.
I guess we're all.
Can I use this one or just, okay, sure. Okay, so it's my good honor to share our works from Athena, which stands for the edge computing by leveraging the next generation networks. So my name is Yan Chen. They asked me to put my introduction here, but I think I'm past this one because I have already been introduced. So let's talk about what is Edge AI. So Edge AI basically is a hierarchy like you can see here. So everything which you are using now, starting from the cell phone to Tesla driving car to laptop, they're basically the edge devices. And the definition of the edge is trying to process the data where the data is generated. So because there are many reasons, such as, for example, privacy, latency, or many others. And on top of this, you have some computing power we can support to the AI, framework, which you can use to process those information. They start with, data center or the edge, we call the edge data center. So you need to deal with a lot of things, such as the deployment of the large model in very short time, very small devices, and running very, very fast. So that's going to deal with something we call the availability functionality, because we deal with a lot of different functionalities running on the different devices, and heterogeneity, efficiency, and also trustworthiness, which our colleagues will talk about it. I want to give a couple of examples just happened in the last year. Those are the technologies we developed, within a year, but introduced a tremendous impact in both academia and the industry. The first one is AWQ, Active Vision Aware Quantization for the Efficient Edge LLM. So basic idea is you're trying to quantize the neural network because you do not need to have floating point to calculate everything which you're going to use on the edge devices, which we know it. But the issue is most of the application require you to fine-tune the model or even retrain the model for the efficiency, which are completely useless in the real, the scenario, because nobody going to allow you to retrain the model since that's be very large and run other things. So a team from MIT and the Song Han's group developed something called the AWQ, which trying to examine the impact of the quantization on the activation component of the LLM and propose the post-training quantization methods that are going to be used widely in the industry right now. So just published within a year, this actually has been generating more than 40 million downloads from GitHub with the 3.3 the 1,000 GitHub stars with the citation is actually more than 1,300, actually more than that. Actually, this the data has been out of date. So this paper received the best awards from the IML last year and widely used in many companies like NVIDIA, AMD, Intel, Amazon, Microsoft. You can name a few which have been using this technologies. Not to mention that, actually this technology was developed by the team, from the group, from the company actually acquired by NVIDIA, also funded by Song Han, last year, spinning off from the Athena with, more than $100 million. Okay, so next one is about the Fed BPT, the efficient federated black box prompt tuning for large language model on the edge. Traditionally, if you want to work, make sure all the devices will work collaboratively, what you can do is you have to let them to sense the data, process the data, to share the gradients you generated, and also do the averaging between each other, and distribute all the calculated the change of the width to the different the large language models such and such. You need to fine tune the model on the edge. However, this will be very costly because usually you can increase the memory usage for about 10 to 12 times if you want to really fine tune the models compared with doing these things on the just purely for inference. So this idea came from you can do the prompt engineering. So basically you add, even not semantically, meaningful the tokens in addition to the prompt you're going to use, and to make sure you can really fine tune the performance of the LLM, to the different adaptation requirement or something we call the personalization. By doing that, you actually reduce, the volume of the data, transfer between the device and the cloud by the 500,000 times, and you can really run those things, which you have to use, for example, 70 gigabyte memory. Now you can run those things on this Shelly, the cell phone with only 2 gigabyte memory. So just after the 3 months, this technology was invented basically by my group. The NVIDIA had already took these ideas, saying this should be, the NVIDIA federated learning platform, for this commercial use. Okay, so the third one is actually, we talk about utilized in the industry, but third one is about the security part. So basically, from the Neil Gong, which is also our colleague from Duke. So basic idea is he's trying to define the prompt injection attack, which is going to allow the malicious user to put some the dangerous content on the website, and the prompt going to pick up those things, as the previous speaker talked about it, and also use this one for this agent or this large language model. Unfortunately, those information can really harm the performance and generate some malicious behaviors. So this paper actually became the rank 40 in the 100 most influential security conference papers in the past 40 years. Just the paper only published last year. So that's become another example to show we're not going to just generate the industrial impact, but also the academic impact too. So last thing I want to show is about, but not the least, is educational practice. So think about how we're going to design the future edge devices. By the way, there's a sound here. I'm not sure if you can, turn on the sound, either by icon. So so traditionally, if people trying to design the edge devices,
other agents,
what
including the searcher, executor, and verifier. Finally, the wiring agent generates the circuit connections. The framework
Okay.
supports multiple IoT platforms like ESP-IDF and Arduino. In this demo, we will use the ESP32 board as an example. First, we start with a natural language task description. Once the system is launched, the analyzer identifies the key requirements and determines
I
the
think-
analyzer summarizes the task, and then the searcher agent begins gathering relevant resources from the web and stores them in the local database. Next, the system automatically sets up the required development environment. Once preparation is complete, the agents begin development. You can observe their reasoning process, decision steps, and tool invocations in real time. After development, the system outputs the compiled firmware along with an automatically generated wiring diagram and natural language wiring instructions. If a physical development board is connected, the system will automatically flash the firmware onto it. Finally, we can have a multi-turn conversation to refine the project. This concludes the demo. Thank you for watching. This video presents the
Can you
IoT
pause
agent
this so I can
demo,
repeat
which
again?
showcases
So the basic idea is, instead we just teach our student, to really learn the different components, how to wire them, such and such. We actually develop an agent, to really, translate the natural language description of what the device or the system they try to develop, and putting this one to the agent. Agent will give you then, the guidance about which component you need, how you can connect them, how you can verify this, how the code will be, written and also deployed to the component. This agent will be used in our course, which as listed here, ECE 55 taught by Professor Qingjun Chen and developed by just a few master students during the summer. And actually, you know what? There's one Fortune 500 company. Look at this. They contacted us saying, "Can you really implement this agent to my product?" So because eventually, this actually, lead to our new companies just registered today, by, our professors and receive a $1 million investment. Okay, so I conclude my talk. Thank you.
Hi, everybody. I'm Zach. I think I'm next up on the slides. Do I have this? Is this guy? Sweet. Okay. I'm the Associate Director of ARNI. What is ARNI? ARNI is Artificial and Natural Intelligence Institute. And so we study neuroscience, cognitive science, and AI and the relationships between them. Who are we? So we're a bunch of people. It's a pretty big group. And so we're grouped into sub-projects and hierarchically structured as well. We come from, let's see, go back. I thought I had a map there. That's okay. Why are we doing what we're doing? Wait a minute. So it looks like we're missing some elements here. Well, ARNI studies a variety of different threads, different thrusts here, which involve neural mechanisms, continual learning, robust, flexible learning, and have a bunch of different application domains. Thank you. I don't know where that one was. Yeah, so there's the application domains. And so we're trying to weave these together to understand what are the principles of intelligence and things that can help both brains and machines. For me, my background, I came from physics and then did some biophysics. It's my PhD, theoretical neuroscience and machine learning. And now I do this thing we call neuro AI. And neuro and AI are nicely connected because of their history and the shared principles. So why is neuro AI special right now? Well, two big reasons. One is that we have this amazing frontier data. So this is an image, reconstructed image of a cubic millimeter of mouse brain that was recently published by our consortium, and it has exquisite detail. And we also know the functional response properties of every one of these neurons. And then at the same time, we're able to use massive compute to build models of this stuff. So frontier models, foundation models of brains, of how brains respond to different sensory inputs, eventually of how we behave. And so then we can try to understand with effectively unlimited data what the structures of those models are and how they help behave. What are their underlying algorithms? So we're trying to reverse engineer intelligent computation. And these kind of inverse models have a lot of connections with the other institutes. So those are fun topics for us to talk about, like theory of mind, as you'll see in the AI Invite group, is basically what scientists are trying to do when they study a brain, right? What is that brain thinking? And we're trying to find core algorithms, which is, I think, a nice connection with IFML, Foundations in Machine Learning Research. Another key ingredient that brains have that other systems don't yet have that we could learn a lot from the brain is our energy efficiency. So the brain, right now, your brain is burning like 20 watts, whereas a GPU is going to burn 500 watts. And if you're trying to get a query from ChatGPT, you're burning 10,000 watts. So how is it that our brains can do so much more with so much less? Whereas machine learning right now is going big, brains go small, and they have better inductive biases. So we're trying to find the inductive biases. And so that connects to AI, the edge computing and Athena that we just talked about. The core of intelligence is about generalization. And so we know already for a long time that neural networks can do anything, but that doesn't mean that they can do that well. They may need a huge number of resources, and it may be really hard to train. And the no free lunch theorem says that it can't be especially good at learning everything. It has to specialize. So what are good inductive biases that we can learn from the brain that are good for our world that we're in now? So we think about this in terms of structures at the small and large scale that have to do with circuits and learning. And so this is what a lot of the people in our institute are trying to understand and develop new algorithms, whether that's little motifs like the right nonlinearity, as you might see in self-attention in transformers, or the right kind of macro architecture, or the right type of learning rules or objectives that you would have at the learning level at micro and macro scales. So we recently created a new course, an online course that you can check out through the Neuromatch Academy. So you can look at neuroai.neuromatch.io. And with that, I'll stop and looking forward to some discussion.
Hi, everyone. I'm Adam Clivens. I'm the director of IFML. We're the Institute for Foundations of Machine Learning. We were in the very first cohort, and we work on the core algorithms and architectures that power the Gen AI tools that all of you use in your workflows. One thing that I've been telling people that I found to be sort of controversial based on the response is that whether you realize it or not, everyone in this room, like your long-term research goal is to come up with a new algorithm. Okay, if you're an algorithms researcher, whether you realize it or not, you may want to train using less data or you do inference faster. You're going to need a new algorithm for that. Maybe you want your model to be more robust. Maybe you'd like to come up with some way to detect watermarks. I mean, that's an algorithmic problem. Maybe you would like your model to be more transparent or interpretable. Again, that will require new algorithms. Or maybe you'd like to come up with a new way of filtering data sets, which is an important algorithmic task, something that we do a lot at IFML. So, I'm a big believer in algorithms, and I think, the next frontier in, AI research will be algorithmic. One question that, when we started thinking about planning for IFML, we were in the first cohort, and, I've been thinking about this since, for 20 years probably, is that, we have this current paradigm for training machine learning models, and that is you come up with an architecture and you run gradient descent. Will we be using gradient descent for the next 50 years, for the next 100 years? Is that it? Is that all there is? Have we stumbled upon like the ultimate algorithm for training our models? I think that's a very interesting question. I mean, you've seen the impact that, changing an architecture can have. Transformer models have really changed the way that people do AI and machine learning. And so I'm a big believer in sort of the impact of, foundational change or foundational innovation when it comes to our choice of algorithm. So what I wanted to do for just the next 4 slides or whatever is tell you just 2 simple examples where I'm very excited about how algorithmic innovation could be very, very impactful. So algorithms for inference and training are still rapid. I believe they're still rapidly evolving. I don't think that we found the ultimate architecture, and I still think we can do better than what we currently have. And I believe, big improvements are still in store. So I think it's still a very exciting time to work in foundations. One interesting question that there's been a lot of attention for recently is sort of discrete diffusion, versus autoregressive LLM. So the current paradigm right now is that LLMs do inference in an autoregressive way. That's just seems to be the way that the best performing models work. But one really interesting question is what about diffusion? Is there some way of having a model that doesn't do inference in an autoregressive manner? So it's sort of filling in tokens in some other order. There was a very interesting paper. Okay, I'm biased. My student in my IFML postdoc won best paper at ICML for a recent paper, investigating exactly this question. Can you use discrete diffusion instead of autoregressive methods for language models? So far there are like 2 interesting caveats. 2 interesting points. One is that you can almost match the performance of autoregressive language models using discrete diffusion by inpainting in a discrete way, but it's way faster. So the inference uses far less power, far less compute resources. So that if we can do inference using an order of magnitude less resources, that's a huge win for all of us who are doing AI. And they've also shown that, the order that you start, filling in tokens really does matter on a variety of like tasks. Okay, so they're more puzzle tasks, like sort of Sudoku type tasks. But for all these tasks, they can come up with new algorithms that are state of the art, that do better than autoregressive models. And so I think it's a very interesting question. Will we start generating text in sort of in a method that is inspired by diffusion? You could imagine a language model, instead of filling in an autoregressive way, is sort of building an outline first and then filling in the finer details of that outline, more along the lines of how we would write something. So I think that's a very, this notion of, will we transfer from autoregressive language models to sort of discrete diffusion based language models? It's a very hot topic and a very interesting area, especially for doing algorithms research. The other one is, for people who know me, I now do a lot of AI for protein engineering. And if you're familiar with this like AlphaFold architecture, last year they kind of awarded the Nobel Prize in part for AlphaFold. What it does is it takes a protein sequence and it figures out what the 3D structure of that protein looks like based on its input sequence. So it outputs the 3D coordinates of each atom in your protein structure. What's very interesting about AlphaFold is it's not like a vanilla transformer type architecture. It actually has its own bespoke deep learning architecture sitting inside of it. Notably, one big component is something called the evoformer. And inside the evoformer is something called triangle attention. And basically, it has to look at, a protein is a sequence of amino acids. It has to look at triples of all amino acids in this protein sequence. So it has this pair representation where you have amino acid versus amino acid, and that's if you have a sequence of length L, that's an L squared matrix, and then you have to do attention across all the rows and columns of that particular matrix, so you get some cubic operation, and it's very slow. And this is a big problem for people who really need to rapidly understand, what certain protein complexes look like. So there's a lot of research. This is from a recently submitted paper by our group, but there's a lot of research. Can you get rid of this type of triangle attention? Can you come up with just a vanilla transformer quadratic time algorithm that can do protein structure prediction? It's still a major open problem. It would be it would have big impact in the field. We have a paper that can do much better than triangle attention. We only need some different primitive called triangle multiplication. But we still don't know yet how to scale everything down and kind of re-implement AlphaFold using a vanilla transformer type architecture. So I think that's, these are just two examples where I think there's a lot of algorithmic innovation that can and will be very impactful.
Okay, well, thanks for the opportunity to speak here. I'm Chen Zhai, representing Invite. I have 3 keywords for you to pay attention to in the title. One is foundation agents, which to some extent was already motivated by our keynote speaker earlier, but I want to emphasize a human-like intelligent agent, general agent that has already had the learning algorithm, memory mechanism built into it, so that you can build an agent by using this kind of foundation agent, which is tied to what Zach talked about, how human brain works. The second keyword is neurosymbolic. This has to do with integration of large language models with a symbolic representation, particularly rules that can govern their behavior. And this is the key to achieve trustworthiness. Finally, the theory of mind, which Zach also mentioned. And then we are approaching from the intelligent agent perspective. How can you build an agent that has a model of user? This is particularly important for Invite when the agent needs to interact with learners. So in order to measure the success, you need to have a model of the learner. If you say something, would it help the student become more persistent or not? So this requires the agent to have the theory of mind. So 3 keywords. If I stop here, those are the 3 keywords that you should remember. Anyway, so I myself work on turning big data into some kind of intelligent tools to augment the human intelligence, help people solve complex problems, decision-making, healthcare, or education, or scientific discovery. Now, this is the vision of Invite. Mostly suggested from our director, Chet Lang, who's here, why the ground vision is to improve learners' non-cognitive skills instead of just improving their math knowledge of physics, but this is to improve their skills of learning to some extent, particularly persistence, academic resilience, and collaboration. We abbreviate it as POC. Right? So, and we want an agent that's shown here to interact with learners in all kinds of learning environment, where the learner model will get the whole picture of the learner's state, mental state, not just cognitive state, but also non-cognitive state. Is the student frustrated, for example? And then we have the intervention module that would use this knowledge to provide just-in-time intervention, say something motivational, and encourage the student to persist. Now, behind these two modules is obviously large language model support, and we use a theory of POC that's building our team to drive this kind of agent. Now, as NSF is designing this kind of AI institute, we use user-inspired AI questions to drive foundational AI research. Now, this panel is more about foundational AI research, but I started with some user-inspired questions that we address. Firstly is how do you simulate a learner? How do you model a learner? This is key to ensure that we know that we are successful. The second is how can we do this kind of adaptive intervention? And the third is how do we integrate the symbolic knowledge theory of POC with large language models? And finally, general questions like how do you build a small language model that's efficient, deployed on edge device, and how do you self-improve? And right, I can easily generalize these to foundational questions for pretty much all the agents. I think many of you could connect this picture, which looks similar to the old picture that I showed you on the previous slide, with your own applications. Basically, any agent that's supposed to use a task would have to do this. You have to model the user. If you want to personalize the service, how do you know you are optimizing the service for a particular user? Well, your object function needs to have a mathematical representation of the user, right? So that's the theory of mind thing. And you need to ensure trustworthiness. How do you know your system is doing things in a predictable way? You have some regular behavior, and that has to be governed by rules. And that has to do with using task knowledge and any expected behavior knowledge to then govern the agent. That has to do with neuro-symbolic AI architecture. Right, so these are the important questions that we address. These are foundational questions. But I'm going to also talk a little bit about the solutions that we are thinking of. Now, this starts from the limitations of foundation models. They are inherently unpredictable. I'm going to show another slide to convince you that. And that means they are not trustworthy. And so we have to have something else to address this problem. And the solution is to build a foundational agent that would extend the foundation model with memory and to use symbolic knowledge, symbolic representation, and plus reinforcement learning to self-improve itself. But foundation models are also limited in their reasoning capacity. That's because they're not using memory rewriting as humans do to do reasoning. They are using patterns-based reasoning. So we need to introduce also rules and using memory to rewriting rules to do the reliable reasoning, and they cannot self-improve themselves, right? So, but the main point I want to make here is that we have to go beyond foundation model to do agent. Fine-tuning is not enough. It's never going to solve the problem. So here's the optimization view of a large language model. It's trying to optimize the construction error of pre-training data, a lot of data. You want to minimize the error there. It tries to minimize the errors on tasks. Right, so you fine tune and you fine tune with many tasks. So as an optimization problem, you're just seeking some parameter settings that would be optimal for all these purposes. But this would incur some trade-off. For example, if you fine tune with a new task, there will be a balance issue. Do you trust the error to emphasize more on the minimization of the errors on new task or the old task? Right? So this is a visualization of the problem, right? Suppose this star represents where the optimal parameters are set for 3 tasks after fine-tuning, right? So in the parameter space. Now imagine you're fine-tuning with another task. What's going to happen? Well, it's going to move the parameters. Now, unless you have infinitely large number of parameters or your parameters space is large, it's going to likely leave the original optimal point. That leads to inevitable forgetting. And this means the behavior will be inherently unpredictable if you have just have the transformer-based neural network. So The solution is to have some kind of agent that would augment the model. It's not to fix the model. It's not to inhibit the hallucination. Hallucination is a generalization capacity. It's desirable. Humans do that as well. But we don't have a problem because we have a system to rule-based system that will govern us. We know at the party we can joke, but in a serious scenario like this, we don't do that, right? So this is a potential architecture that we have designed to achieve this kind of goal. I don't have time to elaborate, but this is a 2025 perspective paper. If you're interested, I can talk to you more about that. But InVite Institute has a lot of other work in these directions. I just want to briefly mention PhD student Adam Davis, who I believe is here, right? So from UIUC, has done a lot of great work on mechanistic interpretability. He tries to open up the language model to see what's going on, to understand the mechanism and use this knowledge to then to change its behavior, to regulate its behavior. Here's a post there as well. I just checked. It's still there. So if you can stop by to check the details. And Amok is a PhD student from University of Florida, and Adam is involved in that work as well. He has led our work on building learner simulators. And our research co-director, Diego, I think, Diego, are you here? Yes, and has done some excellent work on using multi-agent framework to integrate the large language models with whole learners. And our project manager, Noah, who is not here, I believe, has done some work on neural symbolic AI in education. So in sum, I think foundation agent is the future of the frontier of AI, and that agent needs to have neural symbolic architecture. It needs to be able to reason about the people, so it needs to have a theory of mind. Thanks.
Okay, so with that, we'll set the stage now for our conversation. I think we'll start with architectures. As foundation models grow in scale and complexity and capability, as you've seen, I'd like to ask each of you what you see as the next frontiers in these architectures, whether it's at the edge, in biologics, or in a human AI interaction. Yuren, you've been leading work on the edge AI, and where computation, things like latency and trust all meet and have to work together effectively. How is edge computing evolving in the face of these evolving models, in your opinion?
Okay, over the past decade, edge AI people trying very hard trying to improve the computing power on the edge devices, trying to deploy the larger and larger model on the device. Unfortunately, the gap between what we can deploy on that device and the size of the foundation model we already have, the frontier one, the gap is keep increasing. So which means, the efforts, particularly just trying to build up the small model running on the devices fail, okay? So we need to find out a way. I mean, there's a more advanced, foundational model which allow us to separate the computation between the edge device and also the data center or the cloud to make sure they can work collaboratively, or we can work together with all the edge devices collectively. Those are maybe two approaches which is going to help us from edge AI.
Yeah, and I think, Zach, your insights on how to be optimally effective at minimal power using the model of the brain is super interesting. And where do you see that potentially as an application on the edge, or as we kind of evolve to figure out what might be next?
Yeah, I think Yuren mentioned a couple of things that I think are really critical for driving the cost. One is data transfer, right? So the fact that you have to put things on the edge and you should only send what you need to.
Yeah.
That's a major driver of energy consumption in a computer.
Yeah.
And in brains, you still have some of these issues, but you have a lot of local computation and local selection of the relevant features. So if we can learn what you need where, I think from brain architectures, that would be really helpful. Another one is that keeping zeros and ones apart is also really costly, so that you don't make any mistakes. Like, oh, that was a zero. No, I'm going to call it a one. The brain doesn't worry about that. The brain makes all sorts of stochastic signals, and it deals with that. So that's another major example where we can learn from biology how to make some better algorithms and architectures. And one final one that I think is really important, which is sort of implicit in transformers and a lot of the other architectures that we're talking about, is adaptability. Right now, transformers and self-attention is something that adjusts the computation based on context, but it does it at a network level. Whereas in the brain, you have adaptation at every mechanism, at every time scale and every spatial scale. And so I think we need to learn that lesson, that there are more complex systems that would allow us to do a lot more if you have the right mechanism for it. It can learn the right kind of things, adjust the right types of ways, and gate and route the computations in a more efficient way.
Yeah, and Adam, on learning theory, do you see a shift towards smarter scaling rather than just going towards larger models, particularly in things like diffusion?
Well, I think that's more of an algorithms question. I mean, it's still unclear, you know, what the right mechanisms are to train, you know, based on the architecture. I think that for me, the question in protein sequences, you know, what I was talking about with AlphaFold, where you want to know, could you come up with a model that just looks at sequence alone, the protein sequence alone, and can figure out the structure? Right now, you know, a big bottleneck, we don't have a model that does that. So AlphaFold has to take the sequence and then compute some very expensive multi-sequence alignment. It has to like do a 1 terabyte lookup, you know, to figure out what sequences are similar, and has to know structures that are similar in that space. So even just the question of modality there, let alone architecture, you know, there's been a lot of work on sort of state space models that operate only on the sequence to figure out if there's some language model that can encode structure. It's still open. I mean, we know from the 60s or 70s that information theoretically, like the sequence itself, contains enough information to extract the structure, but we don't have the architecture or the algorithm to figure that out. So I think, you know, achieving that would be very interesting.
Okay, thank you. Yeah, and I think you know, if we segue into the energy that goes in behind that, Zhang, you talked a bit about this, but looking forward, you know, as we talk about efficiency in terms of hardware or compute, a lot depends on how efficiently you use that information. What do you see as a key strategy for making AI more, not just energy efficient, but potentially data efficient as it goes forward from whether that be on the circuit level or with the algorithm itself, or potentially on like an architecture system proposed as you showed in your research?
Yeah, so I think in terms of data efficiency, that just means how can we learn from fewer data, you know, efficiently, learn from as little data as possible. I think humans can learn from a few examples and then generalize well. I think that has much to do with humans' symbolic knowledge, some kind of model of our world, how it works in the world. And that kind of model is intuitively represented in a symbolic manner. And we can leverage this kind of symbolic-based world model to make inferences, and then can explain why this is a positive example, why that's a negative example. And that explanation invokes a lot of kind of symbolic knowledge paths that can allow us to learn more efficiently. So I would say one possibility is if we can have effective neural symbolic architecture, it would likely allow us to learn efficiently from small amount of data without requiring purely inductive reasoning based on data. That's one, I think, possibility. We've actually done some work in another way by simplifying language to simulate how children learn from the environment, right? So if we can train a small model that can be especially useful for edge devices, and those agents only need to do specific tasks. There's no need for the agent to know everything. And so how do we build such a small model? And one strategy is to use simplified language, just like children learn from very simplified language. And yet the language is sufficient to express instructions that the agent should master. So by simplifying the language, the training data, we have a paper that shows that you can actually improve pre-training, and the performance is better than if you just train the small model with larger but noisy, kind of more complicated data. So that's another strategy.
Okay, yeah, Zach.
I think one thing that is underappreciated is when we're comparing humans to machines and we say, oh, we learn this or we learn that, or children learn this, we're actually not comparing apples to oranges, because we as humans have learned from billion years of evolution, and we've been trained on all of our ancestors' experience as well. So what we start with as babies is not what we start with an out-of-the-box machine learning algorithm. So our machine learning algorithms have to recapitulate evolution, which is a different kind of problem and a much bigger, harder problem that may require the right kind of curriculum. So I think that that's an important thing for us to keep in mind. And I'm curious to hear also from you to what degree you think symbolic is really critical. I love symbolic thinking, and I think it's going to give us some very important stuff, specifically in language and reasoning domains. But you have Moravec's paradox, right, where language and symbolic reasoning probably only evolved in the last like 0.1% of our, of life and intelligence. And all of the rest of it is learning how to navigate like an agent, right, in a world that is complicated and all of this other knowledge that is not symbolic. So how do you think about the relationship between those two and how important that is for AI going forward?
Yeah, so excellent question. I think that's a reason for our two institutes to have more collaboration, I guess. Well, yeah, so first of all, I think we can't solely rely on symbolic knowledge, and that has already been proven, right? So the symbolic AI has not been able to be robust and to be general. But on the other hand, the trustworthiness of AI requires symbolic reasoning. And I kind of quickly rushed through the explanation at the talk. The reason is just because what makes the system trustable? It has to have predictable behavior. What is a predictable behavior? Well, it's a behavior that will recur in a predictable way. That means that behavior is governed by a rule. Now, with a pure transformer-based large neural network, there's no way to enforce the rule. I have no way to say, never say word X. It just doesn't work that way, right? You have to train the model with all kinds of data to kind of avoid saying that kind of word. There's no guarantee. So I think that means in order to have a trustable AI system, we must have some way to somehow inject this rule. And the rule must be stored in the permanent memory, persistent memory, so that it doesn't get updated. It's a rule that we want you to follow. It should be stored in the memory, the fixed memory, not updated. That's why I say there's the need to have an agent instead of the foundation model. And they work together in this way. Now, how do they integrate? That's really a big question. And how do we evolve into a state where we somehow learn symbolic representation? And this is some question that I've discussed with many participants here. And this is a fascinating research question, I think, between our two institutes and many other institutes. I think we should study this foundational question. It's possible that the symbolic representation has started from the need to have language for communication, which gives the species survival advantage. For example, if you see lion and then you shout lion, and then in your brain, there's some kind of association with lion, that kind of sound with the visual stimulation activation of neurons. The receiver will associate the scene with the sound as well. There's some grounding happening. Next time, if that receiver decides to say lion again, it needs to make a decision. Is this a lion or not? That decision is a binary decision, and that forces some kind of simplification of representation, if you want. And then that leads to some symbolic representation called a lion. And that could be the starting point, but then that's beyond my knowledge.
I think one of the hot test beds for, whether you need symbolic reasoning is AI for math.
Yes.
Where there's no evolutionary pressure to solve math puzzles.
Yeah.
As far as I know.
And they're expressed in symbols.
Yeah, and they're expressed in symbols. But there's a huge effort to use Lean, to integrate Lean into methods for solving open problems. And so there are tools that use formal theorem provers to kind of help the LLM figure out what steps it should take to solve a particular math problem. But then there are also, OpenAI's paradigm is that you don't need a symbolic theorem prover, and you don't need any formal theorem provers, that just regular old LLMs with the proper supervised fine tuning will crush all of the math problems. And they seem to be doing very well. So I think that's interesting. One sort of kind of cool caveat that's under the radar is that most of these, as far as I know, a lot of these certainly Lean has not been verified. So like there are bugs in Lean. So you could end up hallucinating statements that Lean verifies that are false. So
Yeah,
that's something to worry
don't
about.
feel OpenAI's view would actually work for complex math problems. We have some study where we stress the large language model with many variables. It's going to fail. The reason is because it's using a pattern-based reasoning. It's a chain of thought reasoning. But mathematicians don't do that. We don't do that. We do reasoning by memory rewriting. So we have rules like if A then B, then we rewrite information in the memory by changing A to B. And if we also have a rule that says if B then C, when we write B as C, etc., we can do this infinitely many times as we want. And this leads to reliable deductive reasoning. This is why the system 2 is slow, because it's sequential. It's updating the memory. Now, these large language models are not doing that. And so there's no guarantee that this will be correct. And some study by some researchers in interpretability has shown that basically the whole large language model is still doing a pattern-based chain of thought. If they intervene in the middle, some steps, changes the conclusion, it's not going to affect the following reasoning steps. That's because the reasoning steps was based on the past history. It's not strictly deductive reasoning. So I think memory mechanism definitely.
Jörn, you had something to.
I think we should pass this topic before we pass the topic. And I want to mention, the reason we are also working on neurosymbolic because we want to have interpretable behaviors for some safety critical application like autonomous driving or such and such. That's why we're also working on that part. Yeah.
Okay, I think we've got time for a few questions. Steve, we have some from the audience.
We have 4, and in fact, you could answer them with a yes, no, or 5 minutes. Take your pick. First one, I may be naively seeing continual learning as updating weights in a constrained way, i.e. constrained optimization. Have we learned how the brain does this?
No. This is actually learning is one of the hardest things to study in neuroscience because you only get one chance to make a first impression. So if you're going to study that process, if you show something new, now it's not new anymore. You try to show it newly again, and it's already been seen. So that process is necessarily different. So that makes it especially hard. On the other hand, I think that there are on the horizon, like visibly on the horizon, and in some cases approaching, some new techniques to measure the synaptic weights, the connections between neurons at scale. That was a massive advance that allowed all sorts of insights when we could measure neural activation at scale, when we could measure many neurons at the same time, rather than poking one at a time with a wire. And so now we have an understanding of how populations of neurons work together to some degree in the brain. Once we get the technology to be able to watch synapses changing at scale, I think a similar kind of change will happen for our understanding of the learning process.
Okay, Alex.
So one question I'm not sure if there's consensus is what is symbolic right now. For example, let's say I have an LLM, but I also give it Python. So the LLM can write Python, like Claude Code, for example, can produce a Python file and call a Python execution, see the output. Do we call that symbolic AI or not?
Yeah, that's a good question. I would think about the symbolic symbolic architecture as having some kind of discrete representation inside the agent. In this case, the Python code, is something that presumably the agent has some kind of knowledge of.
No. So there's two things. There's the LLM. The LLM spits out text.
Right.
And then there's a separate component that after the LLM says, please run this code, and it says execute file, and then you stop the LLM. There's no LLM anymore. You execute the code, and then you give back to the LLM context the output of the code.
Yeah.
So the agent is not the LLM. The agent is only, it contains, that's how Claude Code and all the modern agents work, right? They have an LLM, but they have also another for loop and other parts in there.
Yeah, so I would say in this case, the agent has some kind of neural symbolic integration.
Okay.
But the
okay.
large
Then it's
language-
already ubiquitous. That's already that's how all the frontier labs are
Right.
training neurosymbolic systems then, because all the even
Yeah.
GPT-5 itself writes code.
Right.
Yeah.
Yeah, that's why I said this kind of integration must happen. Now, the interesting scientific challenge here is, can we then build a larger neural network model to take care of this workflow so that we don't use, for example, LangGraph, that kind of language to program it. That could be automatically acquired, and that part is unsolved. That part requires us to understand our brain better.
I think that in an LLM, we might have some things that seem to represent symbols, but they're not manipulated as symbols. They are manipulated through the collective action of neural networks, and the enforcement of rigid rules, which I think is often associated with symbolic reasoning, is not there. We might have pretty close to rigid rules, but mathematicians make sign errors and factors of 2. I don't think we use rigid rules either, but we have a loop in the environment that allows us to check and verify. But at the same time, I think it is beneficial to try to impose rules and self-monitoring of how those rules are applied, even in a fundamentally non-symbolic machine, to make it more and more closely aligned with the kind of rules that we think we should think with.
All right, next one. Can we imagine an energy budget approach in AI development where models are designed around fixed power limits like the brain?
Well, from edge computing or even from neuromorphic computing perspective, that is our ultimate dream, to have this energy efficiencies at the same level as the human brain can bring to us. As we just mentioned it, human brain does not have a data center to connect to the human brain to do any decision, right? So similarly, yes, we should have this goal.
I think it's pretty natural to incorporate that into an objective function as a kind of regularizer. I think it's usually not done because our primary goal in AI has been performance, not performance per energy. But now we're seeing that, oh my gosh, we're burning so much energy. Let's actually include that into our objectives. And I think that there is some degree of including that in part in our objectives as we try to make machines that learn from less data, that use less memory, that reside on edge devices. I think there's maybe an implicit regularizer for the algorithms that we use, but we can make it more explicit, and that can help us find better solutions.
Yeah.
Something in between, like the mixture of experts architecture would have some modularized architecture of neural networks that could help us achieve potentially energy efficiency by activating only part of that neural network, which would be a little bit similar to how human brain works.
There's another aspect to this, which is that when we're thinking, we actually have regulation of our resources. We have interlocking constraints. So if you want, you can think longer. If you need some time, give me another second, right? And so having dynamic allocation of resources, I think, is going to be something useful. And you already see that in LLMs, right? You can use different models if you want to think deeper or think longer, et cetera. So that dynamic allocation and self-monitoring, I think, is something that's going to be integrated into agents that have sensors, not just of the external world, its environment, but also of its internal environment.
All right, Jay, that's it.
Okay, join me in thanking the panelists for this thought-provoking and interesting conversation. Thank you, everyone. Much appreciated. That concludes this topic.